Well, certainly it would be true that two distinct planes in R cubed are either parallel to each other, meaning they never intersect, or if they do intersect, they would intersect in a line. And if they intersect in a line, then there would be an angle between them. And we can find that by using, this is actually the way to find the angle between vectors in two-dimensional space. Except it's not vectors, it's vectors normal to the planes. But yeah, that's kind of the same idea. The cosine of the angle between the planes is normal vector dot normal vector divided by, actually absolute value of normal vector dot normal vector divided by the length of normal vector 1 plus length of normal vector 2. And I guess if you think about it, there's no reason why the cosine of an angle between 0 and pi, or if you want to go between 0 and 180 degrees, is always positive. Because if the cosine was negative, if you're in quadrant 3 or quadrant 4, then there'd be a shorter way, you know. And so you would always get an angle between 0 and 180 or 0 and pi if you want. Okay, the two planes are perpendicular if the dot product in this numerator is 0. Now, why would that be? Because the cosine of the angle between the planes is 0, means the angle between those planes is pi over 2, and that's what you call perpendicular. Okay, so the two planes are parallel if a normal vector of one is a multiple of a normal vector of the other. Of course, that's what it means. And so I've returned from my phone conversation. Two planes are parallel if a normal vector of one is a multiple of the normal vector of the other, and of course that would be because they're parallel. If the normal vectors are parallel, then the planes are certainly parallel. Okay, let's get to a little example. And my example is going to be this. Find the angle between the planes. Also find the line of intersection of the planes. That's a harder problem. But finding the angle between the planes shouldn't be too terribly bad. Okay, we need to find the angle between these planes. Well, one normal vector would be 3i plus 2j minus k. One normal vector would be 1i minus 4j plus 2k. And so, I hope I've done that here. Yeah, here's one of them, 3i plus 2j. Here's the other normal vector. And now that I have these two normal vectors, if I find their dot product, that would be 3 minus 8 minus 2. So 3 minus 10, negative 7 in the numerator, except recall that this is absolute value, so call it 7. Over the length of this vector, that's the square root of 14, times the length of this vector, and that's the square root of, let's see, 1 squared plus 4 squared plus 2 squared, square root of 21. So absolute value of negative 7 over the square root of 14 times the square root of 21, and if you do a little bit of elementary algebra on that, 1 divided by the square root of 6. Okay. Thinking if you put square root of 14 square root of 21 together, the square root of 14 is square root of 2 times square root of 7. This is the square root of 3 times the square root of 7, so that 7 and the 7 in the numerator cancel out. You get 1 over square root of 2 times square root of 3, which is 1 over square root of 6. Okay, that's the cosine of the angle. Did we say find the angle? Yes, we said find the angle between them, so I guess it's now easy to say angle between them is angle whose cosine is 1 divided by the square root of 6, okay? So there, this is the angle between the planes. Now, how do you find the line of intersection? Because if these two planes intersect, they intersect in a line. How do you find that line? And we will do this by solving a system of equations that has infinite solution set. And if we show them the infinite solution set as parametric equations, then we in fact have found our line of intersection. So here's the story. This I've done in a very cheap and easy way. I just use row reduced echelon form, that's what this stands for, of this 3 by 4 matrix. It's the augmented coefficient matrix, and got this. But you know, if you want to see it done piecemeal, I could show you that. First, switch row 1 and row 2. So make this row 1, -4, 2, 0, and make the second row 3, 2, -1, 7. So 3, 2, -1, 7. Okay, now let's see. I need to wipe out this 3 here, so I'll say -3 times row 1 plus row 2. That's the operation, and when I do that operation, I will have -3 times this add to this makes this a 0. -3 times this add to this makes this a 14. -3 times this add to this makes this a -7. And -3 times this add to this remains a 7. And then I would say, well, how about we take this row and multiply it by 1/14. So the second row, that's going to be 1/14 times row 2. So then our matrix will come out. Sorry, my space is running here a little shy. So this will be 1/14 times this is 1. This will be -0.5, and this will be +0.5. As you can see, we're looking pretty much like this one, except it's not quite the same yet. But then I can make this into a 0 by multiplying 4 times row 2 and adding it to row 1. 4 row 2 add to row 1. Please, no more phone calls in the middle of this. So let's see, if I did that, I'll just do it here. 4 times this add to this makes this a 0. 4 times this add to this, wow, makes that a 0. 4 times this add to this makes this a 2. And now I have, okay, and that was doing it by hand. Here it is, row reduced echelon form, done by machine. So now that I know that, see, Z can't be solved for, right? So we say Z is an arbitrary thing like T. So since we can't solve for Z, we can say Z equals T. The second row says Y minus 1/2 T equals 1/2. So add a half T to both sides. Y equals 1/2 plus 1/2 T. And X, of course, equals 2. So that is the equation of the line of intersection of those two planes. Or maybe I should say this is the parametric form for the equation of the line that is the line of intersection of those two planes. It would be very difficult for this one to find another form, because I can't solve the first parametric equation for T. So, enough for that example.